German generals stared at their radar screens in disbelief. 300 Allied bombers had simply vanished. Not shot down. Not scattered. Vanished. The green phosphorescent glow of the radar displays showed nothing but chaos, thousands of false returns, meaningless noise, electronic ghosts where there should have been clear targets. The officer commanding the station grabbed the telephone, his hand trembling. "Her general, the entire screen it's impossible. We've lost them all." On the other end of the line, silence. Then a voice, cold and furious. "Find them. Now." It was July 24, 1943. Operation Gemara was underway, the Allied bombing campaign against Hamburg. But something had changed. Something the Germans had never encountered before. Their sophisticated radar network, the technological pride of the Luftwaffe, had become useless in a matter of minutes. And the man responsible for this catastrophe wasn't a general, wasn't a spy, wasn't even a soldier in the traditional sense. He was a physicist. A quiet, brilliant man who had proposed an idea so simple, so ridiculously low-tech, that military commanders had initially laughed at him. But on that night, while German radar operators watched their screens dissolve into meaningless static, Joan Struthers' insane idea was rewriting the rules of modern warfare. If stories like this fascinate you, subscribe, because the most unbelievable part of this one is still ahead. 6 months earlier, in a cramped laboratory at the Telecommunications Research Establishment in Malvern, England, a team of scientists faced an impossible problem. Allied bomber losses over Germany were catastrophic. Every night, RAF Lancaster bombers flew into German airspace, and every night, German radar stations tracked them with terrifying precision. Flak batteries knew exactly where to aim. Night fighters intercepted them with brutal efficiency. The mathematics were simple and horrifying. At current loss rates, Bomber Command would run out of crews before Germany ran out of cities. Joan Struthers was not supposed to be the one to solve this problem. He wasn't even working on radar countermeasures. He was researching electromagnetic propagation, the physics of how radio waves traveled through the atmosphere. Dry, theoretical work. Academic. Safe. But Struthers had a habit of thinking sideways, of seeing connections others missed. One afternoon in December 1942, he was reviewing German radar frequencies when something occurred to him. The Würzburg radar, the backbone of German air defense, operated at a wavelength of about 53 centimeters. He stared at that number for a long moment. 53 centimeters. Half a meter. The size of a piece of paper. The size of... He stood up so quickly his chair fell backward. His colleagues looked up, startled. Struthers didn't notice. He was already pulling open drawers, searching for something, anything made of metal foil. The idea was absurdly simple. Radar worked by bouncing radio waves off metal objects. Aircraft were large metal objects, so they showed up clearly on radar screens. But what if you filled the sky with thousands of small metal objects? What if you created so many radar returns that the real aircraft became impossible to distinguish from the noise? What if you could blind German radar not by destroying it, but by overwhelming it with false targets? Struthers found what he was looking for, a roll of aluminum foil from the laboratory kitchen. He cut strips roughly half a meter long, matching the wavelength of the Würzburg radar. He crumpled them slightly, just enough to create irregular shapes that would tumble through the air. Then he walked into the office of his superior, Dr. Robert Cockburn, and dropped the strips on his desk. "This," Struthers said quietly, "will make German radar worthless." Cockburn picked up one of the strips, turning it over in his fingers. "Aluminum foil." His tone was flat, skeptical. "You want to defeat the most sophisticated air defense system in the world with kitchen foil?" Struthers nodded. "Not defeat it. Blind it. Each strip will create a radar return equivalent to a bomber. Drop a few thousand strips per aircraft, and their screens will be completely saturated. They won't be able to tell the difference between the real aircraft and the false returns." Commanders laughed at him, until they saw the numbers. Cockburn didn't laugh. He was silent for a long moment, staring at the crumpled aluminum in his hand. Then he said, "We need to test this. Immediately." Within a week, Struthers and his team were conducting experiments at an RAF testing range in Scotland. They dropped bundles of aluminum strips from a Wellington bomber while ground-based radar operators tried to track the aircraft. The results were even better than Struthers had predicted. The radar screen filled with hundreds of false returns. The real bomber became completely invisible, lost in a snowstorm of electronic noise. The military codenamed the countermeasure window. The concept was approved for production in January 1943. But there was a problem. A terrifying problem that had nothing to do with physics or engineering. If the Allies used window, the Germans would immediately understand the principle. They would copy it. They would use it against British cities. London, already scarred by the Blitz, could face renewed bombing campaigns with British radar rendered useless. Winston Churchill himself intervened. The decision to use window was frozen, locked in bureaucratic limbo. Security concerns outweighed tactical advantage. Struthers watched in frustration as his invention gathered dust in storage facilities. Every night, more bombers were shot down. More crews died. And the solution sat in warehouses, unused, forbidden. But by summer 1943, the strategic situation had changed. The Allies now had radar-guided night fighters of their own. British air defenses had improved. Intelligence reports suggested the Germans had not yet discovered the window principle. Most importantly, Allied bomber losses had reached a critical threshold. Something had to change, or the entire strategic bombing campaign would collapse. On July 15, 1943, Air Chief Marshal Arthur Harris authorized the use of window for the upcoming raid on Hamburg. Bomber crews received bundles of aluminum strips with minimal explanation. "Drop these over the target," they were told. "1 bundle every minute." No one told them why. No one explained that they were about to deploy the most effective radar countermeasure in history. Joan Struthers wasn't on any of those bombers. He remained in England, waiting for reports, wondering if his idea would actually work in combat conditions. He had run the calculations 100 times. Theoretically, it should work. But theory and reality were often brutally different in war. July 24, 1943. 11:47 p.m. The first wave of RAF bombers approached Hamburg. In the bellies of 791 Lancaster, Halifax, Stirling, and Wellington bombers, crew members opened the bundles they'd been given. Aluminum strips. Thousands of them. Following orders they didn't fully understand, they began dropping the strips through flare chutes. 1 bundle every minute. The strips tumbled into the night sky, catching moonlight, falling slowly, each one reflecting radar waves exactly as designed. In German radar stations around Hamburg, operators watched their screens in growing confusion. Returns were multiplying. Dozens became hundreds. Hundreds became thousands. The clear, organized picture of incoming bomber formations dissolved into chaotic noise. Radar operators frantically adjusted their equipment, thinking the systems were malfunctioning. Controllers shouted contradictory orders. Night fighter pilots radioed in, demanding vectors to the enemy, receiving only confusion in response. General Major Joseph Kamhuber commanded the German Night Fighter Defense Network. He was in the operations room when the reports started coming in. "All radar stations reporting massive interference," an operator said, his voice tight with stress. "We're tracking thousands of returns. It's impossible to determine which are actual aircraft." Kamhuber leaned over the plotting table. The map of Hamburg was covered with markers, far too many markers. This wasn't a raid. He didn't know what this was. But this is the moment no one in the entire war ever saw coming. While German defenses floundered in electronic chaos, RAF bombers flew through the night, almost unopposed. Flak batteries fired blindly, unable to calculate accurate trajectories. Night fighters circled uselessly, their airborne radar sets equally blinded by the metallic cloud now filling the sky. The bombing run proceeded with devastating precision. High explosives and incendiaries fell on Hamburg's industrial districts, residential areas, and port facilities. The city burned. Of the 791 aircraft that attacked Hamburg that night, only 12 were lost, a loss rate of 1.5%. Previous raids on similar targets had averaged 5 to 6% losses, sometimes higher. The difference was window. In a single night, Struthers aluminum strips had reduced bomber losses by 2/3. In military terms, this was revolutionary. In human terms, it meant hundreds of aircrew who would have died that night instead returned to their bases. But the true impact of window went far beyond that one raid. Over the following nights, as Operation Gemara continued, the Germans tried desperately to adapt. They modified radar frequencies. They trained operators to look for patterns in the noise. They developed new tactics for night fighters. Nothing worked. The physical principle was too simple, too fundamental. As long as metal objects were falling through the air, German radar was compromised. The firestorm that consumed Hamburg between July 24th and August 3rd killed an estimated 42,000 people and left 1 million homeless. Historians still debate the ethics of strategic bombing. But no one debates the effectiveness of window. It had worked exactly as Joan Struthers predicted. His strips of aluminum foil had accomplished what years of previous countermeasures had failed to achieve. They had broken the German radar network. The Germans, of course, did exactly what Churchill had feared. Within weeks, they had analyzed captured window strips and understood the principle. They began producing their own version, codenamed Double. By late 1943, both sides were using metallic chaff in aerial combat. But by then, the strategic advantage had shifted irreversibly. The Allies had months of unrestricted bombing operations. Months when their bombers could strike with relative impunity, while German defenses struggled to adapt. Joan Struthers never piloted a bomber. Never dropped a bomb. Never fired a shot in combat. But his contribution to the Allied victory was incalculable. Window didn't just save bombers, it changed the fundamental equation of air warfare. It demonstrated that technological superiority could be defeated not through matching complexity, but through elegant simplicity. The most sophisticated radar network in the world had been rendered useless by strips of aluminum foil. After the war, Struthers returned to academic research. He rarely spoke about his wartime work. In the scattered interviews he gave later in life, he seemed almost embarrassed by his fame. "It was just physics," he would say. "Basic electromagnetic theory. Anyone could have thought of it." But that wasn't true. Many people could have thought of it. But only one person did. The principle of radar chaff, metal strips designed to create false returns, remains in use today. Modern military aircraft carry chaff dispensers as standard equipment. The strips are now more sophisticated, cut to match specific radar frequencies, packaged in cartridges that can be deployed automatically. But the fundamental concept is identical to what Joan Struthers sketched on a notepad in a British laboratory in 1942. There's a glass case in the Imperial War Museum in London. Inside it are several strips of crumpled aluminum foil, yellowed with age. A small placard identifies them as original window strips from the Hamburg raid. Most visitors walk past without stopping. They're looking for tanks, aircraft, weapons, the dramatic artifacts of war. Few pause to contemplate these unremarkable pieces of metal. But those strips represent something profound. They represent the moment when one man's refusal to accept, impossible, changed the course of history. They represent the power of thinking differently, of questioning assumptions, of seeing solutions where others see only problems. They represent the reality that sometimes, the most effective weapon isn't the most powerful or the most complex. It's the one that exploits a fundamental truth about how the world works. German radar operators on duty that night in July 1943 would later describe the experience of watching their screens dissolve into noise. "It was like going blind," one said. "We could hear the bombers overhead. We knew they were there. But we couldn't see them anymore. Our eyes had been taken away." That's what window did. It didn't destroy German radar. It didn't jam the signals. It simply filled the German radar operator's vision with so much meaningless information that the meaningful information became invisible. In the years after the war, as radar technology advanced and became more sophisticated, engineers repeatedly confronted the window problem. How do you design a radar system that can distinguish real targets from chaff? The solutions involved computer processing, pattern recognition, Doppler filtering, layers of complexity added to overcome a simple physical principle. Modern radar systems can now largely defeat conventional chaff. But they can only do so because enormous resources have been invested in solving the problem that Joan Struthers created with kitchen foil and basic physics. Share this story, because forgotten ideas deserve to live forever. The legacy of window extends beyond radar countermeasures. It established a principle that resonates through modern warfare. Electronic warfare is as important as physical combat. The electromagnetic spectrum became a battlefield. Today's military conflicts involve elaborate contests of sensors and countermeasures, jamming and anti-jamming, stealth and detection. All of it traces back, in part, to those strips of aluminum tumbling through the night sky over Hamburg. There's a deeper lesson here, one that transcends military history. Joan Struthers succeeded because he approached the problem from an unconventional angle. He wasn't trying to build a better radar detector. He wasn't trying to jam German signals. He was thinking about the fundamental physics of how radar worked, and he realized that the system's strength, its ability to detect metal objects, could be turned into a weakness. This is the pattern of revolutionary ideas. They don't come from incremental improvements to existing solutions. They come from reconceptualizing the problem itself. Struthers didn't ask, "How do we improve our bombers' defenses?" He asked, "How does radar actually work, and can that principle be exploited?" That shift in perspective made all the difference. In the chaos of World War II, with its massive battles and dramatic turning points, it's easy to overlook moments like this. A physicist in a laboratory. A simple experiment with foil. A bureaucratic decision to deploy an untested countermeasure. But these quiet moments mattered. They mattered to the bomber crews who survived missions they otherwise wouldn't have. They mattered to the strategic bombing campaign that helped break German industrial capacity. They mattered to the course of the war. History isn't always written by generals. Sometimes it's written by physicists who refuse to accept that a problem is unsolvable. Sometimes it's written by people who see a piece of aluminum foil and imagine a way to blind an empire. Sometimes it's written in laboratories and testing ranges, in calculations and experiments, in the patient work of understanding how the world works and finding ways to use that understanding. The night of July 24, 1943, was overcast. Cloud cover obscured the moon. The bombers flew through darkness, visible only to each other and to the radar operators trying desperately to track them. But the aluminum strips falling through the sky caught what little light there was, glinting faintly as they tumbled downward. To any observer on the ground who happened to look up, it might have seemed like a strange metallic snow, falling upward through the beams of searchlights. That image, metallic snow falling through darkness, each piece reflecting light and radar waves, creating confusion and chaos in German defense networks. That image captures the elegance of window. It wasn't brute force. It wasn't overwhelming firepower. It was intelligence applied precisely, exploiting a weakness that the enemy didn't even know they had until it was too late. Joan Struthers died in 1984, largely unknown outside specialized military history circles. There's no statue of him. No aircraft carrier bears his name. Most people who benefit from radar chaff technology today have never heard of him. But his idea persists. His strips of aluminum foil, refined and improved but fundamentally unchanged, still fall from military aircraft whenever radar threats emerge. Sometimes, history isn't written by generals, but by the people who refuse to accept impossible. Sometimes the most powerful weapon is an idea so simple that it seems absurd. And sometimes the course of war changes not through great battles, but through quiet moments of insight in laboratories far from the front lines. Joan Struthers had one of those moments. And on a dark night over Hamburg, 300 Allied bombers vanished from German radar screens. Not because they were destroyed, but because one man understood physics better than anyone else in the room. The aluminum strips fell silently through the darkness. German radar operators stared at their useless screens. And the course of the war changed, not with a weapon, but with an idea. Sometimes, the most powerful force in history is a mind that refuses to accept impossible.